In this unit, we'll examine the mass flow rate of a gas that can be squeezed through a nozzle. We're going to find that once a certain point is reached, it's impossible to increase the mass flow rate by increasing the pressure difference across the nozzle, a phenomenon which is known as choking of the flow. Let's consider the situation where we have a high pressure tank containing gas with a stagnation temperature of T0 and a stagnation pressure of P0. This gas vents through a converging nozzle into ambient air. The exit area of the nozzle is AE and the exit velocity is VE. If possible, the stored gas will be expanded and accelerated to the point where the pressure at the nozzle exit, PE, matches the pressure of the ambient air, PB. If this doesn't occur, there'll still be a pressure gradient in the flow which will induce it to accelerate further. Let's determine the mass flow rate escaping through the nozzle. The mass flow rate is given by the product of the density, velocity, and area at the exit of our converging nozzle. We want to express this in terms of the stagnation conditions in the reservoir and the exit pressure PE. To do this, we first multiply and divide by the stagnation density ρ0 and use the fact that the velocity is equal to the product of the exit Mach number and the sound speed. We're then going to further multiply and divide by the stagnation sound speed. So this becomes exit Mach number times AE over A0 times A0 multiplied by our exit area, and we'll label this equation 1. Now for an isentropic flow, the stagnation pressure is constant, so the ratio of our exit stagnation to static pressure is going to be equal to 1 plus gamma minus 1 over 2 times the exit Mach number squared to the power of gamma over gamma minus 1. We can solve this for the exit Mach number. It's going to be equal to 2 over gamma minus 1 times our pressure ratio to the power of gamma minus 1 over gamma minus 1 all to the power of 1/2, which we'll label equation 2. Now in order to find these exit to stagnation property ratios here, we can just make use of the isentropic flow relations. The density ratio is going to be equal to the pressure ratio to the power of 1 on gamma, while the sound speed ratio is just equal to the square root of the temperature ratio, which is nothing but the pressure ratio to the power of gamma minus 1 over 2 gamma. So if we substitute equations 2, 3, and 4 back into equation 1, we obtain the desired expression for the mass flow rate in terms of those stagnation properties and the exit pressure PE, and we're going to label this equation 5. Let's examine what happens to this mass flow rate if we keep the conditions inside the tank fixed and lower the back pressure surrounding the tank. The mass flow rate, normalized by some constants, is plotted in blue versus the ratio of the pressure inside the tank to the back pressure. When this ratio is 1, there's no pressure gradient to drive the flow from the tank, so the mass flow rate is 0. As we decrease the back pressure, so the ratio of the tank pressure to the outside pressure increases, the mass flow rate rapidly increases in response. This continues to a pressure ratio of just below 2 when the mass flow rate reaches a maximum, and then it decreases slowly at higher pressure ratios. Plotted in green is the Mach number that the flow at the nozzle exit must reach to have this stagnation to static pressure ratio. If we examine where this maxima occurs, we see that it corresponds to a Mach number of 1. So we see that the mass flow rate increases while the flow is subsonic, and then decreases if the flow became supersonic. However, we only have a converging nozzle, where the exit is the throat. So it's physically impossible to produce a supersonic Mach number. Thus, the supersonic portion of these curves cannot occur. Instead, once the flow at the throat reaches the sonic state, it remains at a Mach number of 1 and a pressure of P star, independent of further decreases in the back pressure. Consequently, the mass flow rate remains constant at its maximum value once the throat is sonic. So we see that once the pressure ratio across the nozzle is sufficient to produce sonic flow at the throat, the mass flow rate is maximized and the flow is said to be choked. It's impossible to squeeze more mass flow out of the nozzle by dropping the back pressure further. In fact, once the flow is choked, the entire flow state at the nozzle exit remains fixed. This implies that the exit pressure will exceed the back pressure. A natural question to ask is, what happens when this occurs? Let's first examine the case where the back pressure and the exit pressure are equal. This animation shows a simulation of a subsonic flow being choked by a converging axisymmetric nozzle and then exhausting into a large volume. Pressure contours are shown on the top and temperature contours are shown on the bottom. After the initial startup process of the flow, we see that the exhaust jet is undeflected once it emerges from the nozzle, as the pressure of the jet and the surroundings are balanced. Further downstream, the shear instability of the jet edge causes it to roll up into a series of vortex rings, which is why the flow is unsteady. On the other hand, if we drop the back pressure so that it's substantially lower than the exit pressure, we see that this pressure difference causes the exhaust to expand outwards once it leaves the nozzle. A complex wave structure forms, resulting in the flow outside being very different from the previous case. However, if you look carefully, you'll see that the flow inside the nozzle is unchanged, which is due to the throat being choked. Let's summarize what we've just seen. Once the back pressure is low enough that the flow reaches Mach 1 at the throat, the flow becomes choked. The mass flow rate cannot be increased by lowering the back pressure any further, so it's maximized. The throat Mach number can also not be increased by further reductions in the back pressure, so the entire flow state becomes fixed and independent of the surroundings. So what exactly is this choked maximum mass flow rate? Since it occurs where the exit Mach number is 1, the exit pressure on the stagnation pressure will just be given by the critical to stagnation pressure ratio, and we derived an expression for this in the previous unit. If we substitute this into equation 5, we obtain a simple expression for the mass flow rate, and we can put this in terms of the stagnation temperature and pressure by using the ideal gas law and our expression for the speed of sound. From this expression, we see that for a given gas, the choked mass flow rate can only be increased by either increasing the stagnation pressure, decreasing the stagnation temperature, or increasing the throat area. While choking doesn't occur in scramjet exhaust nozzles, the fuel injectors in scramjets are almost always choked. So this is an important phenomenon to understand if you're interested in studying scramjets. This brings us to the end of the videos for the isentropic flow section of the course. In the next unit, you'll put what you have learned to work by analysing the thrust produced by a scramjet nozzle.